Solve one problem on critical radius of insulation to find out first insulation radius for which the rate of heat flow is same as that when the pipe is uninsulated. Second, insulation radius for the highest rate of heat flow. Now we will read the given question. Dry and saturated steam at 120 degrees Celsius is flowing through a 31 mm outer diameter steel pipe with K is equal to 70 Watt per meter Kelvin with 2 mm radial thickness. In order to minimize the rate of heat flow of the steam, the pipe is insulated by asbestos with K is equal to 0.3 Watt per meter Kelvin. Outer surface is exposed to surrounding air at 30 degrees Celsius. The surface conductance on air side is equal to 15 Watt per meter square Kelvin and steam side is equal to 500 Watt per meter square Kelvin. Assuming unit length of pipe. First question. For what value of radial insulation the rate of heat flow is same as that when the pipe is uninsulated? Second question. Calculate the highest rate of heat flow and corresponding insulation thickness.
Let us understand the given data with the help of diagram. Here pipe with thickness is given. So we have to draw here the circular cross section of the pipe. So what is the diameter of pipe? So diameter of the pipe 31 mm. So we will first find out what is the inside radius. So R1 is equal to 15.5 mm. That is this diameter divided by 2. Then the thickness of pipe is also given, that is equal to 2 mm, and when we add this thickness to this R1 then we will get R2. So R2 is equal to 17.5 mm. So we will show this R1 and R2 in this diagram. So here is R1, that is for inside radius of the pipe, and this is R2 for the outside radius of the pipe, and this is the thickness. Now conductivity for this material is also given. So we will say K1 is equal to 17 Watt per meter Kelvin. So we will mention here K1. Then steam temperature is also given. So this steam is flowing inside this pipe. So steam temperature is 120 degrees Celsius. So we will say this is T1, that is equal to 120 degrees Celsius, and we will mention here as a T1. So this steam will work as a fluid. So here this steam conductance is also given, that is 300 Watt per meter square Kelvin. Now this steam temperature is T1, so steam conductance we will consider as a H1, and H1 is equal to 300 Watt per meter square Kelvin. So it is given, so we will mention in the diagram. Now surrounding temperature is given. So this surrounding temperature is also considered as a fluid. So here it is given 30 degrees Celsius. So we will say here temperature T2 is equal to 30 degrees Celsius. So we will mention here temperature T2 for the surrounding air, and the air conductance is also given 15 Watt per meter square Kelvin. So here temperature is T2, that is suffix 2 is used, so we will consider here this conductance as a H2. So this is the data given, and we have to plot this data in this diagram. Now what is the first question? The first question is that we have to find out the value of the radius of insulation for which the heat flow is same when the insulation is not provided. So how to find out this value? So for that we have to first find out what is the value of heat flow when the insulation is not provided. So if we observe this diagram, here is only steam is flowing inside the pipe, then here is radius R1 and R2 for the steel pipe, and here is the air temperature as well as heat transfer coefficient that is provided. So we have to first find out what is the value of Q for this diagram. That is, this diagram is for when insulation is not provided. Now we will solve this problem, or we will find out the value of Q by using the electrical analogy method. So for that we have to first understand how the heat transfer process is taking place for this diagram. Now we will consider the direction of the heat flow. So this is our assumption. So we will consider the direction of heat flow from this inside of the pipe towards the outside. So we will show this also, that is the direction of Q. That is, the direction is to the outward direction. Now we will consider, here is the fluid, that is the steam in pipe, which is at 120 degrees Celsius. So here the resistance due to convection heat transfer process is there. So this resistance is nothing but R1. So we will mention here, inside the pipe there is resistance R1 that is present. Now the heat is transferred through this thickness, that is the pipe thickness is given with conductivity K1. So again the resistance for the conduction heat transfer is taking place. So we will consider this resistance is R2. Then from this outside surface of the pipe, the heat is transferred to the air. So again there is the convection heat transfer process is taking place. So we have to mention the resistance due to convection heat transfer. So I will write here as a resistance R3. So these are the resistance R1, R2, R3. So heat is getting transferred one after the other. That is R1, R2 and R3 are in series. So while drawing the electrical analogous circuit, we have to show these three parameters in series. Now in between which temperature this process is taking place? So this process is taking place in between this temperature T1 and T2. Now what is the direction of Q? So direction of Q is from inside towards outside. That is, initial temperature is T1 and final temperature is T2. So we have to take temperature difference as a T1 minus T2. So we will show here. Then here is R1, R2 and R3. Now we will move for the calculation. Here pipe is given but its length is not given. We will consider this pipe as a cylinder and we will apply the formula for the cylinder while the calculation of resistance R1, R2 and R3. Now the length is not mentioned, so in solution we will consider it L. Now what is the resistance R1? So resistance R1 is inside the pipe due to convection heat flow. So we will apply the formula 1 divided by H1, 2 pi R1L. So H1 is 500, 2 pi. Now this R1 is given in millimeters. So we have to convert it into standard unit, that is meter. 15.5 into 10 raised to minus 3 into L, that is equal to 0.021 by L Kelvin by watt. Now we will move for the next resistance R2 due to conduction process. So here K1 is mentioned. So we have to take here that is the conduction K1, that is conductivity K1 is mentioned in the question. So we have to take here as a K1. So R2 is equal to ln R2 by R1 divided by 2 pi L K1. So we will put the values. So ln R2 and R1, the values are there, both are in millimeter, but in the numerator and denominator this millimeter will be getting cancelled. So 17.5 by 15.5 divided by 2 pi L into 70. So answer is 2.75 into 10 raised to minus 4 by L Kelvin by watt. Now we will move for the R3. So R3 is for the convection process with H2. Now here 1 divided by H2, 2 pi R2L. Now this outside surface of the pipe is in contact with air, which is having radius R2. So we have to take here, that is 1 divided by 15 into 2 pi into 17.5. So this is also in millimeter. So we have to convert it into meter. So 17.5 into 10 raised to minus 3 into L. So answer is 6.06 by L Kelvin by watt. Now we will calculate what is the heat flow. So heat flow, that is Q, but this is the case of bare pipe, that is the pipe without insulation. So for this condition, pipe without insulation, we will consider here the suffix 1, that is we will take here the addition of all these resistances, because in series we will say summation of R1 is equal to R1 plus R2 plus R3, and therefore Q1 is equal to delta T by summation of R1, that is delta T divided by R1 plus R2 plus R3. Now we will not calculate this, because we will again move for the second condition, that we have to find out the value for insulation thickness, for which the heat flow will be same as Q1. Insulation is provided for the asbestos material. So we have to show here this is the insulation with the help of this circular cross section, and the radius from the center line we have to show as a R3. Now conductivity for this insulation material is also mentioned in the question. So this conductivity we will consider as a K2. Now what is the question? So the rate of heat transfer without insulation that we have calculated in earlier section, that is Q1, which is equal to rate of heat transfer after insulation. That is, we will consider this rate of heat transfer as a Q2. So we have to show Q1 is equal to Q2, and for this condition we have to find out the value of R3, that is the radius of insulation. Now we will understand what is the relation in between this rate of heat transfer to the radius of insulation. So for that, on this vertical line we will put the value of Q, and the horizontal line here is radius of insulation. Now as this radius of insulation is getting changed, then here is the line. In this way this value of Q is also getting changed. Now we will show here the radius of pipe, that is the inside radius R1 and outside radius R2. So here is R1 and this is the R2. Now when R2 is there, then what is the value of Q? So we have to draw here for this radius R2, we will draw here one vertical line, and we will join this line up to this point of intersection with this graph. And then to find out the value of Q, I will draw here one horizontal line. Now this value of Q, so here is the point of intersection. So this is the value of Q without insulation. Without insulation. Because this R2 is for the outer radius of the pipe. Now what is the question? We have to find out R3 when Q1 is equal to Q2. So this Q without insulation is nothing but Q1. Now if we add the thickness after this R2, then this thickness is for this insulation. So if I draw here the horizontal line, then here is the point of intersection. So this point of intersection is for this Q without insulation, and here this Q with insulation. Q with insulation. Now if I draw here, or if I draw here one vertical line, so here is the point of intersection. So this point is nothing but for R insulation. So here is R3 that we have to find out. So here this is Q1, so I will draw here, right here Q1, and here is Q2. So for this condition, that is for question, Q1 is equal to Q2, and we have to find out the value of R3. Now we will solve this problem by electrical analogous method. Now we have to understand how the heat transfer process is taking place. So we will decide the direction of heat transfer in the same way as in earlier or previous question, that is we will consider here from the center towards the outside direction. Now R1 and R2 are same because here inside the pipe there is the resistance due to convection heat transfer. Then here is the thickness of pipe, resistance due to conduction heat transfer. So this R1 and R2 are same, but after this pipe outside radius of the pipe there is the insulation thickness that is provided with radius R3. So here is also conduction process is taking place. So R1, R2 and R3 is used, so we will take the next resistance, that is R4. So R4 is there. This R4 is for the resistance due to conduction in this insulation is taking place. And again at the outer surface of this insulation there is air is in contact, where the convection heat transfer process is taking place. So we will consider the R5, that is the resistance due to convection heat transfer. So we will consider here the R5. Now if we observe the pattern of heat transfer, heat is transferred one after the other. That is R1, R2, R4 and R5 are in series. And this heat transfer process is taking place in between this temperature T1 and T2. That is the temperature of steam and temperature of air. So we have to take the temperature difference as a T1 minus T2. So we will show here. So here is R1, R2, then R4 and R5. And here temperature difference is T1 minus T2. Now R1 and R2 we have calculated earlier. So we have to calculate now only R4 and R5, and then we will find out the value of Q2. Now we will calculate R4. So R4 is the resistance due to conduction in the insulation material. So with the help of diagram we will apply the formula. R4 is equal to ln R3 by R2 divided by 2 pi L K2. Now this R3 value that we have to find out. So we will take R2 in standard unit, that is 17.5 into 10 raised to minus 3 meter, divided by 2 pi L, and value of K2 that is mentioned 0.3. Now we will simplify this numerator. So ln R3 minus ln 17.5 into 10 raised to minus 3. Now we will again simplify this. So denominator answer is 1.885 L. Now again we will solve this, that is ln into 17.5 into 10 raised to minus 3. So ln is provided in the calculator and we have to take as a 0.01755. That is minus 4.045. So I will simplify here as a which is equal to ln R3 minus 4.045 divided by 1.885 L. Now this minus and minus will become plus. So instead of this minus minus I will write here ln R3 plus 4.045. Now we will move to calculate R5. Now this R5 is in contact with the outer surface of the insulation which is having radius R3. So what is this resistance due to convection heat transfer? That is 1 divided by H2 2 pi R3L. So H2 value is given. So when we solve this we will get 0.0106 by R3L. Now from this diagram or the electrical analogy circuit we can say that this R1, R2, R4, R5 are in series. So we will write here as a suffix 2 for this summation of R. That is summation of R2 is equal to R1 plus R2 plus R4 plus R5. So what is the value of Q2? Now if we observe in previous case and in this case the temperature difference T1 and T2 is same, that is delta T. So we have to take delta T divided by summation of R2. Now we will show Q1 is equal to Q2 and we will find out the value of R3. Now we will show Q1 is equal to Q2, that is delta T by summation of R1 which is equal to delta T by summation of R2. Now we will put the value of summation of R1 and summation of R2. So here are the values. So this delta T is getting cancelled and we can transfer this right hand term to the left hand side and this left hand term to the right hand side. So it will become R1 plus R2 plus R3 is equal to R1 plus R2 plus R4 plus R5. Now when I transfer this whole left hand side to the right to the right hand side, then it will become R1 plus R2 plus R4 plus R5 minus R1 minus R2 minus R3. So this R1 R2 is getting cancelled and the term will become R4 plus R5 minus R3 is equal to 0. Now all these resistances that we have calculated and we have to put its value. So here is the equation, that is ln R3 plus 4.05 divided by 1.885 L plus 0.0106 by R3 L minus 0.606 by L is equal to 0. Now we have to find out the value of R3. So here this is the complete term that we will transfer to the right and we will put the value of R3 by trial and error method. So we have to take this value of R3. So standard unit is meter. So from this meter value in meter we have to consider any random value and then by trial and error we have to solve this. So what is the value of R3? So R3 is 3.75 millimeter. So this value in millimeter is given. That means approximately we have to take the value of R3 in meter, that is 0.031. That is given and then this equation that will be getting solved. So this is the value of R3, but question is that what is the thickness of insulation? So thickness of insulation, that is we have to find out this value, that is R3 minus R2. So 30.75 minus 17.5 which is equal to 13.25 millimeter. So from this diagram we can say that for R3 is equal to 30.75 millimeter. That is when we provide this this thickness 13.25 millimeter thickness for this insulation, then the heat transfer will be exactly same, that is the without insulation. Now we will move to the next question. We have to find out what is the highest rate of heat transfer. Now if we observe this graph for this rate of heat transfer with respect to radius of insulation, then here this graph varies in this way and at particular point there is the highest rate of heat transfer. So when I observe for this point, here is the value of Q, that is the Q max, and if I join this point to this horizontal line, then this is the value of R, that is the radius of the insulation. Now for this value of maximum Q, we will consider here this radius as a critical radius of insulation, that is RC. Now for this RC we have to draw here one diagram. So we will show here this radius of insulation, that is the critical radius of insulation RC, and the resistance due to the conduction heat transfer through this RC is, we will consider here as a R6. And then if this RC, that is the surface of this critical radius of insulation, is in contact with this outside or surrounding fluid, then the resistance due to convection is known as R7. Now if we observe this diagram, here R1, R2, R6 and R7 are in series because the heat transfer process is taking place one after the other. So how to calculate maximum value of Q? That is, we have to take the temperature difference. So this whole heat transfer process is taking place in between this temperature T1 and T2. So we will take T1 minus T2 divided by summation of R, that is R1 plus R2 plus R6 plus R7. So R1 and R2 we have calculated earlier. Now we will find out this R6. Now for this R6 we will apply the formula, that is the resistance due to conduction that is taking place, and here the radius of insulation is the critical radius of insulation. So how to calculate this RC? So this RC is depend on the value of conductivity K2 that is provided for the insulation material and for the convection heat transfer process. So from this RC there is the heat is transferred due to convection process. So here convective heat transfer coefficient, that is H2. So K2 by H2, that is equal to 0.3 by 15, which is equal to 0.02 meter. Now R6 is equal to, we will write here the formula, that is RC by R2 divided by 2 pi L K2. So ln 0.02. So this value we have to take in meter. So in the denominator R2 value also we have to take in meter, that is 17.5 to 10 raised to minus 3 divided by 2 pi L into 0.3. So when we solve this we will get 0.0708 by L Kelvin by watt. Now R7. So R7 is the resistance due to convection heat transfer 1 divided by H2 2 pi RCL, because this whole surface is in contact having radius RC. So when we put the value, then we will get 0.5305 by L Kelvin by watt. Now it is easy for us to calculate Qmax. So we have to put all these values and then we will get the answer, that is 144.56 watt by meter. Because L is not given or not mentioned in the question, so we will consider here L, that is length of the pipe, that is equal to 1 meter. So answer is 144.56 watt by meter.